Hello, everyone. Come on in.
I wanted to talk
Yeah. I listen to you,
um,
Richard. Go ahead.
the lockdown browser or whatever. It said I need access code.
Yes. So if you're taking it, you're supposed to be taking it proctored, and your proctor knows the access code. You're not allowed to take it on your own at home.
Well, I emailed you and said I want to take it, for the lockdown browser.
Gotcha. I was wondering why you were saying that. So you're actually, I've had a couple people that email me or sent me text messages. You send me a text or an email?
I emailed you
Okay, let me check that.
because I was asking you when it was the deal was supposed to be test, and I was like, well, I'd rather take it, at home because I really don't have transportation like that. So if I really could take it at home, that would be the best option for me.
Gotcha. So you're obviously in the 242 class, and did you have a excuse for not taking it this past? No, that's right. Yeah, that's right. You were supposed to take it Tuesday. Did you have a,
Yeah, I was supposed to take it like I think it was Tuesday. And then I asked you, I was like, yo, can I take it, like the lockdown browser since, what I'm saying?
yeah,
But
it requires a lockdown browser and the respondus monitor. Do you have access to both of those?
yeah.
Obviously you have a webcam. I see you're talking to me. Sorry.
Yeah, but
Yeah.
that's all I was telling you. I was like, well, I don't really have a car, so like
That's no problem. I made one up specifically for the one student that had reason to do that. I just didn't realize you were one of those. Let me check and see.
yeah, I saw it was for Logan or whatever. So
Yeah,
that's how
you can take that one. And let me send you a password. You can do it right after class. You will need a mirror of some sort. You have to put some kind of mirror behind you so that if I'm looking through your cam, I should be able to see your computer screen. And more specifically, more importantly, I need to be able to see like what's going on under your desk, that sort of thing.
oh,
Uh,
okay.
that's why I switched and didn't let people do it this semester. So
Okay.
I'll go ahead and send you the password right now. All right, I sent it to you. It's not all the letters are lowercase. It automatically capitalized the first one by accident, but all the letters are lowercase, and it does have that special symbol on the end
Okay.
that you'll see in the email. Okay,
All right. Thank you.
sorry about that, Richard.
It's okay. But yeah, I'm sorry I didn't like tell you like last class because I had to do something during class, so I had to leave early. So I was going to ask you about it. So
No problem. Let me just make sure I have it open long enough for you. You're gonna take it tonight, is that correct?
yeah, tonight.
Gotcha.
Is
So
it
yeah,
due before 11? Because
it's
I did
actually no.
for
You can
10.
do it as late as tomorrow.
All right,
I
okay.
made up an entirely different one for Logan and you from what everybody else did. So it's not a big deal that you're taking a little bit of time afterwards. So yeah, you can take it tonight or you can take it tomorrow.
All right, thank you.
You're welcome, bud. Anybody else have any questions? You'll notice my voice is going in and out, so I might have to cut the class short. I've got sort of three problems that I wanted to work for you guys regarding chapter 19. And then I might jump into 20, but more than likely I'm just going to call it a day just because my voice keeps coming in and out. So, anybody else have any questions before we get started? All right, so last time I talked to you about conduction. That's when two objects are actually touching each other like that. And then if this one's the hotter object, then the kinetic energy of the molecules in this one is larger than the kinetic energy of the molecules in this one. And when they're touching, there's not like a container that the molecules stay in. The molecules, where they stop moving, is sort of on average, is the line that is the edge of the actual object. So, what literally is happening is molecules from this guy are bouncing off of molecules from this guy. And in so doing, it's sort of like a Mack truck bumping into a Hyundai or something. So the Hyundai will start speeding up, assuming it hits properly, but in the case of molecules, it will. So the Hyundai will speed up. The Mack truck will lose a little bit of speed, and that's not necessarily a change in temperature yet. What ultimately happens is the molecules, after they're hit by the faster molecules, they become a little more energetic, and then they run into their own molecules, and then on average, all the molecules become a little bit faster and therefore have a little bit more kinetic energy. Therefore, the whole temperature of the colder object went up. Similarly, in the hotter object, that molecules that actually hit the slower molecules, or at least the lower kinetic energy molecules, they'll slow down a little bit as well. Then they'll run into other molecules within their own group and slow those down. And on average, eventually, all the molecules will slow down a little bit. So the hotter object will become a little cooler. And that keeps on happening until basically the two sets of molecules all have the same kinetic energy, which means they are all at the same temperature, and therefore they're in thermodynamic equilibrium, and conduction stops. Basically, heat stops flowing from the hot body to the cold body because now they're both the same temperature. At that point, of course, you then have the air around it. If the air around it's not the exact same temperature as the temperature of the two objects, then they'll start exchanging energy with the surroundings. And normally those surroundings are a little cooler than both of the objects, in which case they'd cool down and eventually reach the temperature of the room. So that's conduction. Convection is basically a good way of thinking about it is sort of like your coffee maker. Oh well, I say coffee maker. I know a lot of people are using like Keurigs and stuff like that, and that's sort of a little different process, but somewhat the same. It's not as transparent. But if you were to open up a coffee maker, what you'd see is the plug comes from the wall and goes into a wire, and then it goes into this little object that's usually like plastic, and it's coated like in silicone or something like that, and that sits down inside of the water that you pour in. That object becomes very, very hot. Basically, it's a heating element like you'd have in a hot water heater, and that becomes very hot. That heats up the water around the heating element, and then that wafer of water around the heating element is now a little bit hotter and therefore a little less dense, because we learned earlier, like in chapter 17, that when you heat something up, it expands. And if it expands, that means it's a larger volume but the same mass, so the density is less. So now that warmed up water will float up to the top and deliver some of its energy to the things up above. That's convection. That is a complicated beast because you're dealing with fluid dynamics and thermodynamics, and uh, there's some ways to simplify talking about laminar flow and stuff like that, but really it's just a nightmare to deal with. So we don't offer any equations on that, but you should know how it works. And then finally, the last type was the radiation, which is how the sun gets most of the energy to us that we get. And that is basically waves of electromagnetic radiation. And the conduction is characterized by dq over dt is equal to the thermal coefficient K times A times delta T over L. Technically, if you call that delta T over L the pressure or the temperature gradient, then the temperature gradient points to a decrease, whereas the dQdt actually goes to the lower temperature. So you sometimes have to put a negative in there if you're really thinking about which direction it's flowing, but I always just calculate magnitude, so it don't matter. So that's one of the equations. Now, the other equation was the equation for radiation. That's called the Stefan-Boltzmann equation. And I wanted to show you a couple examples with that. So does anybody have any questions before we get started on those examples? All right, so let's imagine a window. So a window has a glass.
Hey, Professor Younger.
Oh,
I don't
y'all
think
want
you're
to see
sharing
this?
your thing. Oh yeah.
I did it again. This is so terrible. I do that all the time. Yeah, thank you for that. Appreciate it. And don't feel bad about embarrassing me. It's my own fault. I get it. I get what I deserve. Shouldn't be a turn old. In my defense, I'm strung out on NyQuil. So a window glass. Our window has a glass pane that is about 0.40 centimeters thick and has K equal to 0.80, and that's watts per meter Celsius degree, which you could also write as Kelvin. On one side of the window, the temperature is, let's say, negative 10.0 degrees Celsius, and it is, let's say, 20.0 degrees Celsius on the other. The window is about 1.70 meters. Oops, I don't know why I put cursor there. 1.70 meters tall and 0.65 meters wide. How much heat is lost per second? Okay, so that's the question. I'm going to do another one in a second where I'm going to do a double pane window that has a wafer of air between it. I will tell you up front that the window is not as bad as it sounds like right here. We're suggesting that it's pretty much cold air, glass, and then warm air. Honestly, there's cold air. Then there's a little thin, unless the winds are really bad, then there's a little thin wafer of air between the window and the coldest of air. And that little wafer of air pretty much stays still and is in fact not horribly quite as cold as the horribly cold stuff. And then on the inside, another window, another little wafer, if you will, of air is on the side, and that pretty much doesn't change because you rarely have winds inside of a house unless you're running a ceiling fan. So those two layers of air on the inside and the outside of the window actually does a little bit more than this is going to suggest. So it's not quite as dire as it sounds, but it does help. And also, when I do the calculation for double pane, the same thing's true. You get another wafer of air outside and another wafer of air inside, in addition to the wafer of air between them. So let's do the solution. So the equation we learned, I like to write it as dq dt instead of q over t, but your book's calling it q over t. I also calculate magnitude, so I don't put negatives in there. But the formula is basically k times a times t hot minus t cold over L. That's just the way I calculate it. They call it T1 over minus T2 or whatever. It doesn't really matter too terribly much. So what I'm going to say is dq dt for this particular window, again, ignoring that wafer of air on the outside and that wafer of air on the inside, uh, that gives me, and I can't access Pearson right now, so I'm locked out of that. I'm going on memory as to what the K value is, the thermal conduction coefficient. I think it's 0.8. If anybody finds out that glass is something different than 0.8, please let me know. You can even Google it. I just didn't have time to do that. So I'm going to say this is 0.80. And as I said, that's watts per meter Celsius degree. And then times the area. And really, everything should be in meters anyway. So I'm just going to put the numbers in there. And the numbers are 0.65 meters times 1.70 meters. And then times, in this case, it'd be 20.0 degrees Celsius minus negative 10.0 degrees Celsius. So that's 30 degrees Celsius. And then all that will be divided by, even though I'm writing it right under the temperature, all that will be divided by 0.40. And actually that's centimeters, so I got to convert that to meters. So let me change that. 0.0040 meters. Okay, so I'm going to go ahead and multiply all the numerator stuff. And I'll give you the answer. I'm not going to write it down separately, but I'll give you the answer out loud. So I'm doing 0.8 times 0.65 times 1.7 times 20 minus negative 10 is 30. So times 30. That gives me 26.52. Actually, I'll go ahead and write it down on top. 26.52. Notice with that, I multiplied it by meters squared. So this is watt meters times meters divided by 0.0040 meters. So now I'm going to divide that by 0.004, and that gives me 6,630 watts. So that's also 6,630 joules every second. Since I asked for the heat loss per second, it might be better to state it as joules per second. In fact, I'm really only using 2 sig figs all here, so this digit and that digit are actually not significant. So any questions on that? All right, now I'm going to repeat it with, so let's say repeat for a double pane window with air. I'll write K is equal to 0.023 watts per meter Celsius degrees. With air between the two panes, identical, oops. Between the two panes, if the air thickness is about, I'm going to say 0.0100 meters. In other words, centimeters. It's a whole centimeter. So now we're going to do the exact same calculation, but this time we're going to do it with the 3 layers. Again, ignoring the wafer of air just outside the window and the wafer of air just inside the window. But we're just going to count glass pane, air, glass pane. And this is where you can see the usefulness of the R value as opposed to the K value. At least the way I calculate it, you can. So what we're going to say is dq over dt is again equal to K times A times T hot minus T cold over L. But we're going to make that a little simpler by writing A times T hot minus T cold over L over K. Because when I do that, I'm actually using the R values. So that's the R value that we know of from, construction, basically. If you just walk into a newly constructed house or building or business or whatever, you'll see there's insulation up, and it's usually fiberglass insulation with like a brown backing that looks sort of like grocery bags. That will be marked like R13 or R19 or R21 or something like that. That's the R value. It's defined to be L over K. And it's actually in weird units. It's in units of, I want to say BTUs. No, it's watts per, well, actually it's like watts per square meter. Or actually, I think it's BTU per square meter degrees Fahrenheit or something god awful like that. Your book explains it in that last section or in that second section immediately after the section on convection. Excuse me, conduction. Sorry. All right. So in this case, we can now say dq. Oops, I need back to green. So I'm going to say dq over dt is equal to. Now in this case, the A is still the same. It's the same for the air. It's the same for the glass. So I'm going to take 0.65 meters times 1.70 meters. Those areas are the same. And then the temperature difference is again going to be 20.0 degrees Celsius minus negative 10.0 degrees Celsius. So, and here's the part where the R comes in handy. It turns out when you have layers, the R values just add. So what I'm going to do is instead of putting the length separate and the A and the K separate, we're actually going to put them one by one. So in the case of the first pane of glass, we've got L, which is 0.0040 meters divided by 0.80 watts per meter Celsius degree, something like that. Yeah, I'm just trying to make sure that works out right. So that works. Okay. Plus the second window, I know I'm not going, actually, let me go ahead and do the air first. So I'll say the air, which is 0.00. In this case, we said it was going to be no 0.1 instead of 0.0. So it's 0.100 meters over 0.023 watts per meter Celsius degree plus 0.0040 meters over 0.80 watts per meter Celsius degree, like that. So that's a little more complicated in terms of calculation, but notice when I have layers on top of layers, all I have to do is just add them in the denominator. That's the beauty of using the R value. Whereas if I was using just the K value, I would have had to do a separate part and just make it a little more confusing. So I'm going to do the 0.65 times the 1.7 times 30. In that case, I get 33.15. And of course, that's meters squared. So that's meters squared Celsius degree. And then all that's going to be divided by 0.004 divided by 0.8 gives me 0.0032. And then plus, that's the two for the window. And then for the air, it's going to be 0.01 divided by 0.023. And that's going to be 0.434. 4348. Now in the bottom here, which hopefully y'all see that that's one continuous line. In the bottom here, those units are going to be basically meters squared per watt Celsius degree. So I could say like this, meters squared per watt Celsius degree. So you see that ultimately all that's going to come out is just plain watts, which is what we want. So now I'm going to take this point or 33.15 and I'm going to divide it by parenthesis 0.0032 plus 0.0032 plus 0.4348 close parenthesis, and that time it gives me 75.14 joules per second. Well, actually, let's go ahead and say it watts. What the heck? And then I'll write it again with joules per second. So you can see there's a huge savings. In this case, we also had, of course, only 2 sig figs on the top because it's 3 for the difference in temperatures, but then 2 for the 0.65 meters. So only the 33 is a sig fig there. And then when I took and added the 0.032 to the 0.032 to the 0.032, or excuse me, the 2.0032s gave us basically to the tenths, hundreds, thousandths, 10,000ths to the 10,000ths place. And then the 0.43 only gave me to the, or 4348 only gave me to the hundreds place, hundredths, th place. So basically adding those all together gave me that figure, which is 0.0032 times 2 plus 0.4348. That gave me 0.4412. So there's only 2 sig figs in that one too. So both of these are only supposed to have 2 sig figs. I know the sig figs don't matter too much, but just to be instructive and show you how they're supposed to be done, I wanted to make sure I include the details of how to figure out the units. The problem with units really is mainly in the adding and subtracting, because when you add and subtract, it doesn't use the number of sig figs, it uses the number of decimal places. And the one with the fewest number of decimal places dictates exactly where it's rounded off at after adding or subtracting. So when you have addition and addition to multiplication, you end up getting problems like that. So hopefully me taking time to show you that helps a little bit. Anybody have any questions on that? So you see, not even counting the actual extra wafer of air, uh, you can see that the double pane window certainly does way better than the single pane window. Of course, I'm not counting the little wafer of air just outside and the little wafer of air just inside in either case. So it's not like I'm doing one unfairly, but you can see I'm losing on the order of 6,600. That's like wasting, I don't know, 6,600 watt light bulbs with a 1 pane window. Whereas the other one, I'm wasting a single 75 watt light bulb. And even then, like I said, there's another wafer of air on each side that could bring it down a little further, just like there's another wafer, 2 wafers of air that could bring the 66 light bulbs down a little bit. But 66 white light bulbs is way bigger than 175 watt light bulb. So you can see the double pane windows are very much worth it. So anybody have any questions on that? All right, let's move on to the next one. So, a human, T equals 98.6 degrees Fahrenheit, walks into an empty auditorium at 68.0 degrees Fahrenheit and feels a little chilly. However, after the auditorium fills, the human feels, oh, uncomfortably warm. Explain. Okay. So what's happening here is the rule is any object with a temperature greater than 0 Kelvin, which you'll learn later, one of the versions of the second law of thermodynamics, or maybe it's third law of thermodynamics, says that you really can't reach 0 Kelvin. So everything has a temperature higher than 0 Kelvin. With that in mind, uh, when I say everything with a temperature higher than 0 Kelvin emits radiation, then you reach the conclusion that clearly everything emits radiation. So it turns out that not only does the human emit radiation, but the air from the room emits radiation as well. So I've got to go ahead and convert the 98.6 Fahrenheit and the 68.0 Fahrenheit to Celsius and then convert that to Kelvin to be able to use, because the formula we're going to use is dq over dt, which I sometimes call L for luminosity, is epsilon times area times sigma times t to the fourth. And sigma is the Stefan-Boltzmann constant, which is 5.67 times 10 to the negative eighth. And that's watts per square meter Kelvin to the fourth. Okay. And the emissivity we're going to estimate to be about 0.7. Okay. So the emissivity is supposed to be between 0 and 1. Your book talks a little bit about how things that are really, really dark are supposed to be closer to 1, and things that are really, really shiny are supposed to be closer to 0, that sort of thing. But what you got to understand here is I have a human being, and that human being has a temperature of 98.6 Fahrenheit, which is markedly warmer than the 70 degrees or 68 degrees Fahrenheit that the auditorium has. The air in the auditorium will, in fact, produce radiation that will be absorbed by the human, and then the human's going to also produce radiation that'll be absorbed by the environment, so that ultimately you get dq over dt total is equal to, notice the interaction with the heat coming from the air into the human and the heat from the human going into the air both have the exact same emissivity, and they have to. That's sort of the nature of it, and your book explains that as well. So we're just going to have one emissivity. We're going to have one surface area, which I'm going to estimate the human body surface area to be about 1.7 square meters. That's a as my daughter likes to call me, that's fun fat. So that's probably comparable to my body surface area, because I'm fun fat. I'm not, grotesque fat yet. I'm fun fat. So anyways, that's my story. I'm sticking to it. So what it would be is this times T body to the fourth minus T auditorium to the fourth. So that's really what we got to use. So first off, I'm going to say 98.6 degrees Fahrenheit is 98.6 minus 32 would be 66.6. And I'll call that Fahrenheit degrees above freezing. Okay. And I also know that 66.6 Fahrenheit degrees basically because the temperature changes in the Celsius scale from 0 to 100 between freezing and boiling, whereas the temperature scale changes from 32 to 212, which is 180 in the Fahrenheit scale, then I can write 180 Fahrenheit degrees over or under 100 Celsius degrees like that, and that'll be a good conversion factor for that. So if I take 66.6, let me double check that too. I'm sometimes make careless mistakes with my arithmetic, but I'm pretty sure I got that right. That's 98.6 minus 32, 66.6. Yeah, that's right. I just didn't remember it being that number before because I thought I would have remembered that. Given the historical significance of the of those three digits. But anyways, I'm going to take the 66.6, I'm going to divide it by 180, and I could divide by 180 and multiply by 10. That'd be fine too. And now I'm going to multiply that by 10, and that gives me 3.7. What the poop? Oh, multiply that by 100. Sorry about that. I forgot I had divided by 180. I was thinking I had divided by 18. If I divided by 18, I have to divide by multiply by 10, but I had divided by 180, so I had to multiply by 100. So that gives me 37.0 Celsius degrees and 37.0 Celsius degrees above freezing, which by the way is 0.0 degrees Celsius, is 37.0 degrees Celsius, or, and here's where you can take 37 and just add that to 273.15 to make it Kelvin. So 273.15 plus 30 be 303.15, and then that'd be 310.15. So that's 310.15 Kelvin. So that's just a refresher on how we say it's pedagogically most efficient way of converting units between Celsius and Fahrenheit. So hopefully that's a nice little refresher. Notice I didn't have to use a formula. I also sort of understood how the process goes. That's kind of nice. I'll do the same thing now for the 68.0. So 68.0 degrees Fahrenheit is, I subtract 30 from that, that gives me 38, and then I subtract 2 from that, that gives me 36. So it's 36.0 Fahrenheit degrees above freezing. So we've got that part. Now I'm going to take that 36.0 Fahrenheit degrees and I'm going to multiply. This time I'll actually use the reduced version. You can see why immediately, hopefully. That's 18 Fahrenheit degrees and 10 Celsius degrees. 36 is actually 2 times 18, so that just gives me 2, and then 2 times 10 is 20.0 Celsius degree. And 20.0 Celsius degrees above freezing is 20.0 degrees Celsius. Okay. So I now have that, and what I'm going to see is dq over dt total is equal to 0.7 for the emissivity, 1.7 square meters for the surface area, and then 5.67 times 10 to the negative 8, and that's watts per meter squared, Kelvin to the fourth. And now I'm going to take, oh, by the way, that is 293.15 Kelvin. So I'm going to take 310.15 Kelvin, and I will raise that to the fourth power minus 293.15 Kelvin, and I'll raise that to the fourth power. Okay, so 0.7 times 1.7 times 5.67 e to the negative 8 is equal to 6.747 times 10 to the negative 8. And notice I've multiplied the meter squared by there, so all I have now is watts per Kelvin to the fourth, and then 310.15 raised to the fourth power is a big number. I'm going to call that 9.253 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the ninth Kelvin to the fourth minus 293.15 raised to the fourth power. Sorry, that's 7.385 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 Kelvin to the fourth there. Okay, so I want to say so I end up getting 6.747 times 10 to the negative 8, and only two of those are sig figs, watts per Kelvin to the fourth times 1.868 times 10 to the ninth Kelvin to the fourth. And that gives me about 126.0 watts, which equals about 130 joules per second, because these two are not sig figs. Okay, so the explanation that I'm pointing to here, though I didn't necessarily state it that well, come think of it, is that each of us, when we walk into an auditorium like that, having a body temperature roughly 98.6, each of us act like more or less a 120, 130 watt light bulb. So once you get an auditorium packed full of people, then each of those is basically a 100-watt light bulb or bigger, and that ultimately makes the room warm up quite a bit. Any questions on that? All right, your book does another problem too, which is pretty good. That's basically comparing the luminosity, which is this dq over dt for the Stefan-Boltzmann law, the luminosity for a star called Betelgeuse versus a star, or our star. It turns out our temperature of our star is about twice as hot as the temperature of Betelgeuse, but Betelgeuse actually puts out about 10 to the fourth, or 10,000, excuse me, yeah, 10,000 times more radiation per second than our star does. Obviously, the fact that our star is twice as hot would suggest that our star should put about 16 times, because 2 times 2 times 2 times 2 is 16. So you'd expect, just based on the temperatures, not the whole formula, but just based on the temperature to the fourth, you'd expect our sun to put out 16 times more radiation than Betelgeuse. But in fact, our sun puts out 10 to the negative fourth times the radiation of Betelgeuse, so way smaller. The only way that you can compensate for that is looking at the Stefan-Boltzmann law. You realize there's really only two parameters that control how much radiation is put out. One is the surface area, and the other one is the temperature. Okay, so we've already established that the temperatures are in the opposite direction, so that the Earth should be putting out 16 times more. But in terms of surface area, Betelgeuse turns out to be really, really large. So if you do that like your book does, what you end up finding out is that the radius of Betelgeuse is something like 3 times 10 to the 11th meters, which is bigger than a astronomical unit, which is the distance from the center of the sun to our Earth's orbit. Uh, I, Generally speaking, the error bars are a little bigger. And I know that because I've taught astronomy for some years, but I will tell you that basically we know for a fact, based on similar calculations, in fact, that Betelgeuse is huge. And if you were to replace our sun with Betelgeuse, it would be so big that the orbit of Mercury would be inside of it, the orbit of Venus would be inside of it. And error bars allow us to say that the orbit of Earth could be in it. But it might not be just because the error bars. But according to that calculation, like your book did, it actually came up with it being inside of the body of Betelgeuse. Okay, so if anybody knows of the constellation Orion, you can go out and look at that. Just for the record, Orion looks like this. You'll look up and you'll see. Well, let's do a red dot first. You'll have a really red, bright star here. Then you have sort of a blue star here, and you have 3 blue stars here, and you have some not quite so bright blue stars here. Then you have another blue star here and another blue star here. And this one's really bright. In fact, this star is called Beta Orionis. And this one is called Alpha Orionis. But it's also called Betelgeuse. And there's a bunch of different spelling. This is transliterated from Arabic. You might think it's a post 9/11, politically correct thing to go back and, call these things with Arabic words. But historically speaking, partly while we had our Middle Ages, where we were not so inclined to build up experiments and science and stuff like that, but rather we were, well, we we were doing the Inquisition, okay, among other things. But it turns out the knowledge and the science that had been created by the Greeks and the Romans had been picked up by the Arabs. And during that period, I say Arabs, I mean people from the Levant and in that area in general, not necessarily only Arabs, but mostly what we would call Arabs. Those people were actually living through sort of like their Renaissance. So they were actually not only taking the science and stuff that the ancient Greeks and the ancient Romans had made, they were building on it themselves. So we ended up getting a lot of names for stars and for areas of science that came from Arabic. That's why we have words like algebra, algorithm, the trig functions. For instance, sine comes from a Arabic word as well. So, anyways, this is an Arabic language. So the most direct way of transliterating it is Beetlejuice, like Michael Keaton in the movie. Okay, this one's also called has another name as well. This one's called Rigel. Now, initially, when we first looked at Orion, and by the way, there is a little star up here, and there's some stars out here as well that sort of make like a shield or a bow or something like that. Uh, But when we first looked at it, it was pretty obvious to most people that the red star was the brightest one in there, and that's why I got the name Alpha Orionis. And Rigel was really the second brightest, so it got the name Beta Orionis. As time went on and technology improved, we were actually able to measure exactly how bright it is. Now, I'll say brightness. Brightness is actually the luminosity divided by 4 pi times the distance squared. This is luminosity, which is that dq over dt, which equals epsilon sigma a t to the fourth. That's what that luminosity is. Now, another interesting fact about the constellation Orion is that unlike constellations in general, the bright stars, these, 8 or 9 very bright ones I just drew up here, are all came from the same nebula. In fact, there's a couple nebula in this little area right here that you can look at just with binoculars. You don't need even a telescope. You can do it with binoculars. But if you have a telescope, it looks even better. You'll see pretty blues and reds and stuff like that of gases. You usually can't see the red too much. You can, if you got a nice telescope, you might be able to with a little bit of timed exposure. But you can always see the whites and the blues, and it looks cloudy. And that's actually an incubator for stars. And in fact, all those 8 or 9 brightest stars in Orion all came from the same nebula. Now, that doesn't mean they're really, really close to each other, because a nebula can be, on the order of light years apart, or light years across. So these guys are all within a light year or so from each other. And in fact, compared to the distance they are away, which I think is around 1,500 light years, essentially all these stars are the same distance away from us. So the brightness that we're comparing is actually the equivalent of the luminosity. So are actually comparing luminosities to each other when we compare Betelgeuse and Rigel. So the fact that they were mistaken initially as Betelgeuse being the brightest and Rigel being the second brightest, and then later when we actually got the technology to measure it, we found out that Rigel was slightly brighter. We historically left the name to be consistent with history, which is Alpha Orionis for Betelgeuse and Beta Orionis for Rigel, but they're actually about the same brightness, but Rigel's a little bit brighter. Because of that, we know, oh, those two stars must have about the same luminosity. Uh, and because of that, we know that the luminosity only depends on the surface area and the temperature to the fourth. And the fact that this star is blue implies the temperature. Let me do a Google search real quick for this. I'm going to say temperature of Rigel. It's about 11,000 Kelvin. Whereas I think the temperature of Betelgeuse is like 2,900 Kelvin. It's saying 3,500 Kelvin. So if you compare T Rigel to the fourth power over T Betelgeuse to the fourth power, you get basically 11,000 over 3,500 to the fourth power. So 11000 divided by 3,500. That's about pi 3.14. And I raise that to the fourth power. That gives me 97.57. But they're about the same. So L Rigel is very close to L Betelgeuse, which means A Betelgeuse over A Rigel should be about 97.57. Notice I put them upside down. because the Betelgeuse has to outpace the 97.57 that Rigel has if it's going to be hotter, if it's going to be more luminous, but it's going to be about the same. So with that in mind, we could say, okay, well, this is assuming the stars are spheres, this would be 4 pi times the radius of Betelgeuse squared over 4 pi times the radius of Rigel squared. So you end up getting 97.57 is approximately equal to the radius of Betelgeuse over the radius of Rigel raised to the 2 power. So that suggests the radius of Betelgeuse over the radius of Rigel is equal to, I got to take the square root of both sides. So 97.56 raised to the 0.5 power gives us about 9.878. So it's about 10 times larger than Rigel. If I look up the radius of Rigel, it tells me it's 34 million miles. That's not really what I want to. The radius of Rigel is about 78.9 times the radius of the sun. So we're looking at basically 780, around 780 times bigger than the sun. So now we can say the radius of Betelgeuse is on the order of 800 times the radius of the sun. And the radius of the sun, of course, is 1.99 times 10 to the, I want to say 11th. Let's look at that real quick. Radius of the sun. That is not the units I wanted. Why are you giving me the wrong units? Why are you giving me the units I hate? 1.99 times. Oh, that was the mass I was thinking of. No wonder. Oh, I kept thinking coming up with 10 to the 30th. And I'm like, that's not right. I think it's that's 10. So 1, 2, 3, 4, 5, 6, 7, 8. So it's about 7 times 10 to the 8 meters. So if I multiply 7 times 10 to the 8th times 800, which is a rough estimate, then I get 5.6 times 10 to the 11th meters, and 1 AU is 1.49 times 10 to the 11th, if I remember. Let's see. One astronomical unit is, 1.49 times 10 to the 11th. Yes. So you can see right there that it is, in fact, its radius is big enough to have the Earth's radius, Earth's orbit inside of it, according to this calculation. So I did the calculation entirely differently than the way the book did. So now you've got two examples, actually 3 examples total of using the Stefan-Boltzmann equation. Anybody have any questions on that? Looks like some people put some chat. Let me check these out real quick. Okay. Okay. Oh yeah. Ramsey was talking about basically when Iraq was sacked in the, I guess that'd be maybe the 1000 roughly, what we would normally call AD, but we now call the CE, the Common Era. I think that was roughly around when Baghdad was sacked. But yeah, we lost a lot of stuff over the Middle Ages, which some people refer to as the Dark Ages. I actually have a book where they call it the Bright Ages. It's some historians talking about all the positive stuff that came during the quote unquote medieval period, are like a lot of naysayers would say the dark ages. But yeah, we lost a lot of knowledge that way. It's kind of terrible, but it keeps happening. I just saw two idiots throwing coffee on the Mona Lisa the other day. Luckily, it was behind glass. Yeah, I completely agree. You should be complaining and trying to get your voice heard about uh, global warming and stuff of that sort. But there's no excuse for destroying artifacts like that. Just keep it away from that. But anyways, so that's basically it. I was going to, like I said, go into chapter 20. What I would tell you guys to do is read over chapter 20 and look for all of the versions of the second law of thermodynamics. So I'm going to write it right here. Everyone should read chapter 20 and write down and name each version of the second law of thermodynamics given by the author. Also, also zeroth law and third law of thermodynamics. So that's probably the most important thing I'm trying to get you guys to learn out of chapter 20 is the second law of thermodynamics, which is super important. And a lot of times it's really what keeps charlatans from ripping us off. So it's important for the skeptical movement. It's important from a scientific standpoint. It's also important for your education because you can find people on the internet that will tell you that the second law of thermodynamics is violated by the theory of evolution. It's not. Okay. So it's something that you really should know as an educated person. So the second law of thermodynamics is something I want you to study. I want you to write it down verbatim from the book along with the name that the book uses for each version. And then your book will mention the zeroth law of thermodynamics. In fact, I think they might have done that in 17 or 18, but definitely look it up and write that down. And it also mentions the third law of thermodynamics. I want you to write those down as well. And then other than that, uh, I would like you to know uh, how to calculate the efficiency of a Carnot engine. So know how to calculate efficiency of a Carnot engine. I mean, you can go hog wild and learn about coefficient of performance and all that stuff regarding heat pumps and refrigerators and all that stuff. That's useful too. But what I care most about is can you calculate the Carnot efficiency of a Carnot engine, and then of course compare that Carnot efficiency for any heat engine. So you need to know how to do that. Know how to calculate the efficiency of a Carnot engine, and know what S equals K ln omega means. So if you have those things covered, then we can blow through chapter 20 and literally less than a class period, and I can jump back into 21, which is really the most important part of the semester is all about electricity and magnetism, which starts in chapter 21. Uh, it's now 6:23 and I'm supposed to keep you till 6:40. I'm going to go ahead and let you go. My voice is failing me already. I think I've given you ample examples and I've warned you what to know next time. So please, please, please take the time to read over that chapter and explicitly get those three topics covered really well, taking notes while you're reading. And read a little bit at a time so you don't, keep losing your interest or whatever, but read a little bit at a time for as long as you can. And then I was just reading the comment, sorry. And then you'll be ready for class on, you guys meet Tuesday, so you'll be ready for class on Tuesday. Good luck for those of you who are taking the test tonight. I know the 241 students that are online are taking it tonight. And I know I have a couple students that might be taking it tonight for the 242. So have a good one. You're free to go. I'll wait for the last person to leave in case anybody has any questions. Thank you very much. So Michael was asking me what good things came out of the medieval period. Uh, yeah, I haven't made it past the introduction of the book yet. My friend is a medieval historian, and it's his field of expertise, and he gave me that book, but he also given me two other books that were way more, quote unquote, way more interesting to me initially. So I've been reading those and haven't read this one yet. So I can't tell you yet, but I, I yeah, I don't know what good came out of, out of the Middle Ages, but we'll figure something out.
I have a question.
Yes.
Um, were you able to look into the homework assignments, like the access on Canvas?
Yes. Yeah, I remember I was speaking with you on was it a text message or an email that I
Yes,
think it was a text message, wasn't it?
text. Yep.
Yeah. Yeah. I can get everything regarding it. I'm not going to be able to get yours, where you did that going off a line and going through the internet to it. I'm hoping that will not prevent me from getting the rest of them.
Well, I just
So,
went to the well, I didn't go straight to Pearson. I went to the Pearson tab that you have and then follow the link to Pearson to the Pearson website.
okay.
It's just, you know how you have chapter 17 in the module section, 18 and 19 aren't in there, or
Right.
any of the other chapters, but they show up on the calendar. So when I tried to click it on the calendar, it gave me that
That's
screen.
weird. I mean, I've got numerous students that have already finished 17, 18, and nobody started 20 yet. And I even got one person that's finished 19. So I don't know why you're not seeing that, but I do know right now I can't do a darn thing. I can't access Pearson at all. It keeps telling me I'm locked out. It
It's
asked me to
okay. I mean,
log
I
in.
still did it. Hopefully, you'll be able to get the grade off of it. But I still did it from following that link from Canvas to Pearson. It's just not done on Canvas. It wasn't done on Canvas, but I did it.
Gotcha. Well, I tell you what, it doesn't matter either way. If you can go into Canvas where you can see your grade on those homework assignments and capture a
Mhm.
screenshot where it shows your name and the grade on those assignments, uh, you can email me that and I'll just copy it over by hand. I don't even have to see it, but if you had the photo of it and tell me what the grade is in the photo, then I can copy it in manually for it because you only did a couple assignments,
Okay.
shouldn't be a big deal. And hopefully it'll come back. But like I said, I can't access anything on Pearson right now. I couldn't do my Pearson app from my phone. It said I was locked out and I had to reset my password. I reset my password twice and it won't let me in. Then I tried going on the internet and trying to directly go to my lab and mastering. It did the same thing. And now it's doing the same thing even through Canvas. Are y'all able to get into Canvas right now?
I can get into Canvas.
Okay. So I don't know why mine is doing that, but evidently there's a problem. I might have to just empty my cache and give that a try. But anyways, you folks are free to
Okay.
go. And like I said, I'll work with you. Don't worry. I'll never let a student, get screwed up by technology. So we'll get your grade right.
Appreciate
I
it.
promise. You're welcome. Thanks,
All
Ramsey.
right. Thank you.
You have a good one.
Bye. You
Bye.
too.
Professor, I spoke with you on the phone regarding my current situation.
Yes, let me stop recording real quick. Hold on a second.